All right. I am now recording. Let the record note that Brianna has either lied about something. So this is officially going on YouTube. Brianna has either lied about getting a flat tire or being sick. One of the two. Yep. So anyways, continuing our conversation about column buckling, just let's do like a quick recap on how column buckling ultimately works. So the idea of column buckling is that due to some slight perturbation in the geometry of the column, for example, a column being like just slightly skewed due to some imperfection or whatever, would result in a bending moment ultimately being present. So this bending moment would then induce, of course, bending, which is our buckling phenomenon that occurs. And that buckling is really going to be, the only way to really solve it is by solving what we get as a differential equation. All right. Now, I said previously, my skills with differential equations were a little bit lackluster. But I think the general idea is you just apply a general solution to the differential equation that you get, and you should just be able to obtain the critical buckling force as a function of the effective length, right? Now, we can solve this for any given number of boundary conditions, which we saw last class. But the general idea was that for each boundary condition, we ended up with the same general answer with some constant k, right? Technically, it was a constant n, but we interpret it in such a way where instead of using the number of curves within the column, we actually use the effective length of each column in order to get a better approximation and better understand how the column is exactly going to buckle. So for example, for a fixed free end, we noticed that the K factor for column buckling was 2. For both ends pinned, the simple answer was just K equals 1, and so on. So let me actually, now that I am looking at it, AISC column. So in a lot of cases, you'll actually see like different boundary conditions just generally being solved. So like here's a good example. This is actually from the AISC Steel Manual. That's the American Institute of Steel Construction. Mechanical engineers or electrical will not likely see this, but structural engineers or civil will see this a lot more often, but this is just a general reference. You can see that there's a theoretical K value associated with different boundary conditions. And then in design, actually, a lot of codes will update this to be like some slightly larger value just to yield a more conservative answer. All right, so that's just the general gist of it. We basically showed last class that these buckling coefficients were again based on ideal boundary conditions like fixed end, pinned. What I wanted to show you guys today, which isn't actually really traditional as part of the column buckling that you would see in practice, or in like your textbook, I should say, is this advanced frames aspect of column buckling. Now, what do I mean by that? That's when you don't exactly have ideal conditions. So for example, in a building frame, you may have 2 beams going into a column, which then vertically translates downwards. Now, the 2 beams are going to provide some type of torsional resistance or rotational resistance, right? But not to a point where it's entirely fixed. So because of that, we have to use these tables, which have been iteratively developed through experimental data to basically determine approximate K values in which would best define the behavior. So it's basically just accounting for the stiffness at joints instead of just assuming an ideal stiffness. So the best way to really show you guys how to use this table, we could look at a frame really quickly. I know this is a little bit hard to see, but Here we've got a W12 by 65, W18 by 82, W18 by 35, and W21 by 48. So all of these are basically just different members, and as we can likely see, there isn't exactly a hinge here that we would consider ideally pinned, because again, there's going to be some resistance, but at the same time, it's not going to be like entirely fixed. So it's going to be somewhere in between. The idea is, how do we determine the correct K value? So what we want to do is ultimately use this equation down here. And this equation, defined as G, are just relative stiffness terms. So it relates the stiffness of columns to the beams. And it's basically stiffnesses of specific joints, right? So, for example, for point A right here, the problem says that the frame's facade is held by a moment-resisting connection as the means of resisting lateral translation, and we're basically just asked to determine the critical buckling force for the given problem. So, what we first need to really do is, first of all, determine what are our G values, because the G's are going to determine what K is. So we could first do GB, all right? That is basically the G value at this joint B. Now, the G value, if you look carefully, is related to the elastic modulus times the second moment area of inertia divided by L. If you guys will notice, this is actually a flexural stiffness term, and this EI, which you guys have hopefully seen in a lot of the deflection equations, we call that flexural rigidity. That's just a general term. All right, so in this case, we basically want the EI over L of all of the columns at joint B divided by the EI over L of all of the beams. All right. Now, how many columns are running into this joint B right now? 1. So the EI over L for joint B would just be the second moment area of inertia of the W14 by 82. The elastic modulus, all of this is steel, so we can imagine E would just cancel out from the problem, right? But I is basically going to be for the W14 by 82. Now, what is it for the W14 by 82? It should be 800 inches to the fourth. That should be for the W14 by 82. Let me just look it up just to be safe. W14 by 82 properties. And for the W14 by 82, and it doesn't, oh, there is it. 881. So, let me just make sure that that's right. I got too many links on here. Get out of here. Dimensions and section properties. Yeah, moment of inertia about the x-axis is 881. All right, so we've got 881 inches to the fourth, and then the total length is 13 feet. Now, what about the beams? We've got a W18 by 35 and a W21 by 48 going into it. So we're going to have two terms in the denominator. For the W18 by 35, let's look that up. W18 by 35 properties. For W18 by 35, the second moment area of inertia is 510 inches to the fourth. and that's divided by 20. I also just noticed when my bonehead forgot to entirely mention this, the type of bending that the beam will undergo is kind of dependent on your I value. So I forgot to mention that the columns undergo minor axis buckling, so that's technically incorrect. That was the IX, so we should be using IY. Did anyone happen to catch what the IY value was for W14 by 82? So that is not the website that I wanted. This one. For a W14 by 82, under minor axis bending, we want to use IY, which I know it's a little hard to see, but it's basically the 148 that's right there. I'll move it to the top of the screen so you can see. So we want to use 148 for that value. All right, and then because the beams are undergoing major axis buckling, now we need a W21 by 48. So let's now just type in W21 by 48 properties. And I believe it's 959 inches to the fourth. Divided by 20. And what we should get is a dimensionless quantity. Let me pull that up. Where's my calculator? Please tell me I didn't leave it at home. Otherwise, I will be relying heavily on you guys to solve these problems. Oh, here it is. All right, so this G value should be, let's see. I get around 0.155. Make sense? Now, what does this mean? This means that the beams are basically very stiff, all right? So it's almost going to behave more as what? A pinned joint at B or a hinged joint at B? What do you guys think?
Two.
You get 2?
2.015.
2 point? Let me see this.
Oh, actually, this is the representation. That's right.
Yeah. So ultimately, it seems like the beams are going to be infinitely more stiff than the actual column subjected to bending in this plane specifically. So when we come to our table, we know that our GB connections are resisted through moment resisting frames. So we're going to use this table because the problem specified moment frame. All right. So we want to set GB equal to 0.15. That's going to put us somewhere around there. All right. So towards the bottom. Let me do it in red. All right. Now, for GA, we need to know what GA would be. In this case, rotation would be entirely allowed, with lateral translation not technically being allowed. So what we would ultimately want GA to be would just be, what do I want to say? It would be ideal. So we would really, I think, want to set GA equal to, I believe it's supposed to be infinity. I believe we're supposed to set that to infinity. And the reason for that is because then the numerator would technically just blow up, because if you guys remember, the beams are on the denominator, which in this case, there's no beams to really provide rotational stiffness. So because of that, you just assume that GA is just infinite. There's no like rotational resistance. So then you take your nice ruler and you just try your best to basically determine an approximate K value. Let's see. There we go. And with this, we get roughly a K value of around 2. Let me see something. This would be for a fixed pinned, which I don't think makes too much sense. Right, because it's a moment frame. Basically, side sway can be inhibited. Yeah. So GA we would just assume is equal to infinity. And so our K value would just be, from what we get, is equal to 2. All right? And then from there, you would just use your basic critical buckling equation that we had previously used and derived for. And that would just be the K value. So really the problem with this is just obviously identifying what K value we want to use. Make sense? I think I just did a horrible job with explaining this. I will try and be a little bit more specific if I decide to give you guys problems on this for like a homework or an exam. But the idea is just, I just wanted to show you guys how the relative stiffnesses of a beam and column really relate to solving the problem. Make sense? All right. Are there any questions at all about anything we covered from chapter 10? Yeah.
Can you go down 2 slides?
This one?
One more.
This one.
Sorry, one more. You don't convert those feet into inches?
The reason being is because the feet cancel out and the inches cancel out. So GA and GB are technically unitless quantities.
Got it.
Yeah, so it's not needed. Now again, you'll notice we didn't account for the elastic modulus in this, and that's because it cancels. But in some instances, if you have a combined concrete frame with steel frame or some other type of composite material, it doesn't just apply directly to building systems. It's applicable to really anything, It's just relating general stiffnesses of joints to one another. That's all it is. Make sense? All right. Any other questions about this? No? All right. So that was pretty much it for chapter 10. Now I want to kind of delve into chapter 3, which is quite possibly my least favorite topic of all time. And that is the topic of torsion. So with torsion, everyone's heard of torsion, right? You guys haven't really seen torsion in statics, but statics does technically apply to torsion. Maybe you guys have seen it in certain problems. You may have just seen it as some of the moments in X, Y, and Z. Torsion can be one of the moments. All right? So the idea is basically when we are looking at circular shafts, which is one of the assumptions that we make, is all of the problems that you guys will see within this chapter, everything is a circular shaft. I cannot give you guys torsion problems for like a rectangular cross section because they are too complicated. I cannot give you guys torsional problems for a triangular cross section. They are too complicated. The only time I may give them is if we end up covering it, but because of how large of a chapter torsion is, most times within the scope of this course, it's only covered for circular regions or circular cross sections. So the idea for solving torsion problems is basically the same as everything else, all right? You take and solve for external equilibrium. Then from there, you can cut sections and analyze internal equilibrium for those sections and calculate stresses, strains, and deformations. So what we need to do is ultimately just show you guys how those stresses and strains look. So we can take a cut through a circular rod subjected to some torque, which will induce torsional stress. We can analyze the internal equilibrium, and from the torque, we get a shear stress that develops. Now remember, what is a shear stress? It's a type of stress that occurs on a sliding plane, all right? If you guys remember from when we went over shear stresses very at the beginning in the semester, it was always just some type of sliding force, the shear force. For beams, the shear force just determined whether the beam vertically displaced upwards or downwards, and then the bending was a byproduct of that shear force. So the shear force is a type of sliding force. In this case, it's also a sliding force, but in a rotational direction. All right. Now, when we analyze the torque, we first need to kind of break it down into looking at a particular section, all right? This is ultimately how we determine the stresses. If you guys recall, when we were finding the stresses on an axially loaded member, it was just the summation of all of the individual forces for some cross-sectional area dA, which is some infinitely small area. And we basically just added all of the stresses to the equivalent areas. So the problem, again, for a circular shaft should be axisymmetric about its z-axis, which is basically, well, I guess depending on which direction you're looking at. So in this case, it might be, the axes would probably be like, that would be y, this would be x, and that would be z. So it's axisymmetric about that z-axis. For some problems, you'll see it's probably the x-axis. It's readily argued that the shear stress is dependent on the radial position, which we call rho. Some textbooks will use C, some of them will just define R. In this case, we'll use rho to indicate the radial position. And the moments of the two systems that we have, just the torque and the shear stress due to some radial position rho, must be equivalent. All right. Now, we can define this as using calculus terms. So the differential of the torque is just equal to the radial position times the shear stress multiplied by the area. Because again, shear stress is dependent on the area, and the shear stress will actually increase as you go further away. And we'll actually see why later on. But we can basically just state that the torque, the total force that's imposed or carried by the member, is just equal to the sum of all of the shear stresses times their areas times their radial position. So again, the shear stress is not uniform across the cross-section. What we'll find is that it actually increases outwards as we go further away from the center of the cross-section, which we'll actually get into in a little bit. But so axial shear stress induced by torsion. The existence of the axial shear components is demonstrated by considering a shaft made up of slats pinned at both ends to discs. The slats slide with respect to each other when equal and opposite torques are applied to the ends of the shaft. What you guys will notice is from this torque, each of those slats will kind of angle upwards some quantity, and that's going to become kind of relatively important to some of our assumptions that we make about the shear stresses and shear strains. All right, so again, like I was saying, those slats, if we were to break those slats up into small little sections, we can consider our little area dA here, which would have to obviously slightly increase radially in one particular angle. One of the assumptions that we make, which should hold true, is the fact that the strain is entirely continuous. It doesn't get broken up based on the type of region that you're looking at. The angle should always be constant, all right? Which is why if we were to look at this case here, you'll notice that in all of these cases, the shear strains would ultimately be different because the orientation of that block would really vary. And again, one of the things that we want to consider for shear strain, if you guys recall, is one of the points at all times should generally remain constant, right? So I would encourage you guys to just look back at your notes from when we covered shear strain. Again, we're dealing entirely with just circular cross sections because it makes the calculations a lot easier, not to mention once you start getting into the realm of non-circular cross sections, you get relatively non-uniform stress distributions in certain regions because of the fact that you get kind of warping behavior. This can kind of be seen by the rectangular cross section where the corners of that rectangular cross section, the shear stresses would actually be 0 because there's a non-uniform stress that increases radially. And that's, again, because of a warping behavior, which is not favorable for calculations. So we don't even look at that. But the textbook does go a little bit into it. It's kind of a special topics type of thing. So if you guys are interested, I would encourage you to look at the textbooks. But it's not anything that I plan on testing you guys on for the exam. All right. Now, we want to look at the compatibility of deformation. In other words, how do we determine our stress and strain equations? All right. Again, we assume that the angle of rotation for every individual small area dA is basically along one continuous motion. You guys will have seen this here, where all of these lines are just one fluid motion. All right. So it's safe to assume that the radial deformation should be continuous. All right. And that's because if you're looking at some small area, like if you were to cut through for your section for equilibrium, the torques should be the same. The only thing that changes is just how much deformation it goes, but the angle of that deformation should be constant. And we'll actually get into problems later on. All right. One example here is just if you guys look at the bottom, deformation is equal to shear strain. The diagram that's kind of shown right now just kind of shows that each strain kind of just increases upwards, but then it's like as if the cut kind of resets. This isn't true because of the fact that our body is all one body and it's not necessarily broken up into slices like that. Like the parts would have to be actually physically broken and cut and not have any interaction with each other. All right, so our angle of twist is what we call that rotation, is basically just a geometric parameter. Where did my notes go? And where did they go? Here it is. So our angle of twist, we can approximate this as just a triangle because we're assuming small angle approximations. So if we were to draw this out in like a 2D sort of plane, we would get a triangle that looks like this. Now, this rotation here is that angle phi. The height of this triangle here is going to equal c times the angle of twist. And then obviously the length of that gray shaded triangle is length L. All right. Now, let's say we wanted to determine what the angle of twist was. Just geometrically, we could solve for that, and we would find that the tangent of phi is just equal to c phi over L, which we just approximate equaling gamma. Again, this is a small angle approximation. If you guys recall from when we had dealt with shear stresses and shear strains, that the shear strain is just equal to the deformation of the member over its original length, right? A good example of this would be if we had a block here and we subjected it to some force V. You guys should recall that this dimension here was delta V, and this was our original dimension L. In this case, our delta V was, gamma was just basically equal to delta V over L. So it's the same thing. We're assuming small deformations, which is why we're able to make this approximation. Are there any questions about this so far? All right. So continuing on, we basically just get that for small deformations, we can write our shear strain as equaling, here C was the maximum radial position, right? But one of the things that I said earlier is that strain radially increases outwards. So in this case, if we were just considering any radial position, that triangle, the only thing that would change is just basically the radial position of that triangle, which in turn allows us to just be able to write the shear strain as just rho phi over L. So instead of just rho is equal to C, we can now generalize it to any radial position that we're interested in. What you guys should notice is that the shear strain is a linear function. Of radial position. And it basically varies at 0 from the center of rotation to basically just C. So in this case, 0 is less than or equal to rho, which is less than or equal to C, which C was what we specified there. C being the max radius of the circle. Now, with this shear strain, we also technically have a shear stress, right? If you guys remember, shear stress and shear strain are related. How are they related? Does anyone remember how shear stress and shear strain are related? Come on. Exactly. So if we recall that G is just equal to the shear stress over the shear strain, we can rewrite this to just basically say that the shear stress, let me just write it as if it was G gamma. The shear stress would just equal G times rho phi over L. All right, and what we'll notice is that similar to the shear strain increasing radially from the center of the circular shaft, the stress will also increase radially from the center of the shaft. One thing to note is that this rule does not change for solid shafts to hollow shafts. The only difference for a hollow shaft is the fact that technically the stress that's between the center of the shaft and the inner radius, there's no material, so there's no stress. But in turn, there's going to be a minimum stress at the position C1, which is the inner radius of the shaft. All right. Now, as you can imagine, similar to how a reduction in cross-sectional area will increase the stress, we're technically reducing the material properties, the geometric properties of this cross-section, so it's kind of safe to assume that by having that hollow section, the stresses in general will be increased because of the fact that it's now no longer a direct solid cross-section. Any questions about this so far? No? All right. So, so far, we've ultimately derived expressions for the shear stress and strain. So for strain, we write this down as basically being gamma is equal to rho phi over L, which again we can write as just being tau over G, right? That's just our general Hooke's law. For stress, we also know that tau is equal to G times rho phi over L, which again was just equal to G times gamma. All right. But there's just one issue. We don't have a way of calculating the stress from an imposed force. So far, all of our stress equations are entirely dependent on knowing a rotation. All right, so let's use equilibrium. If you guys recall, we can calculate the force in the shaft, which in this case will be the torque in the shaft, using the function T is equal to the integral of the radial position times the shear stress at said position times the small area dA. All right, so we have T from equilibrium T is just equal to the integral over the area of rho, not T, rho tau, the radial position, times the shear stress, all multiplied by dA. Let's replace some terms. We get that T is just equal to the integral of over the area of the radius times the shear stress, which is just going to be G rho phi over L dA. All right. Now, the area is a function of the radial position. You guys would agree with me, right? So we can't take rho out of the integral. But G, phi, and L, we can take those out pretty easily. So T is just equal to G phi over L times the integral over the area of rho squared dA. Does anyone know what this is equal to? You guys may have seen it in statics where it's might be like x, y, r squared dx, dy. You may have seen something like that. What does it look like? Moment of inertia. But there's just kind of one small issue with that, and it's the fact that due to twisting and the way that the equation is kind of formatted, we call this the polar moment of inertia. Have you guys heard of that before? This is sometimes referred to as a term J, which is equal to the polar moment of inertia. And I believe in either most or all cases, J is just equal to Ix plus Iy. So it's just a summation of the second moment areas of inertia. Now this polar moment of inertia is with respect to the center of the shaft, all right? So expanding on this, we end up getting an equation for torque is equal to G phi over L times J. But here's the thing. In most cases, we're given a force, and we may want to calculate how much the bar extends, or in this case, rotates. So we could just rewrite this to then just be phi, the angle of twist, our unknown quantity that we want to generally solve for, is equal to TL over GJ. All right. it's kind of, okay, now it's already kind of messed up a little bit, but this should be phi here. And then all of those equations should be the same. All right. Now, J for a circular cross-section, if you guys were to solve that integral, you would basically find that the polar moment of inertia of a circular cross-section is given by this equation here. J is equal to pi over 2 times the outside radius to the power of 4 minus the inside radius to the power of 4. If it's obvious that if you don't have an inner radius and it's just one solid shaft, then this A term just kind of cancels out to 0. All right. So you treat it basically very similar to if you were subtracting areas or second moment areas of inertia. It functions the same way. All right. So this is just solved through that integral. And this is basically just a recap of all of the equations or other equations that we can basically derive from everything that we kind of discussed so far. One thing you guys will notice is basically just everything is just kind of like some recap of something that we have already discussed. Are there any questions so far about anything that we have discussed thus far? Nothing about the derivations at all or the assumptions that we make? None? All right. Best way to show you guys how to make this stuff work, give you guys an example problem. All right. You guys will notice that a lot of these problems are very similar to the axial problems that we had dealt with in class. All right. The equations are synonymous, just now you're dealing with rotation instead of axial or shear. All right. So, given a torque of 2 kilonewton meters and given that a shear modulus of 80 gigapascals is specified, we want to determine A, how much the end of that rod twists, and then B, the minimum shear stress that is in the rod and the maximum. All right? So the first step of this would just be to determine all of your material and geometric properties. In this case, we have our material properties already specified of G equals 80 gigapascals, but we don't know all of our properties. So let's recall that phi is equal to TL over GJ, just to calculate the end twist. We have G, we don't know J. So let's calculate J. J is just equal to pi over 2 times the outside radius, which in this case is going to be 60 millimeters divided by 2, so 30 millimeters to the power of 4, minus 40 millimeters divided by 2, which is 20 millimeters. All right. From this, let's see, pi over 2 times 30 to the power of 4 minus 20 to the power of 4. This gives us some outrageously large number, 1.021 times 10 to the 6 millimeters to the 4th, which when you do the conversion equates to 1.021 times 10 to the negative 6 meters to the 4th. Now, for this case, it's relatively simple because guess what? If we wanted to do sum of the forces in the, the moment about z direction, or sum of the torques, we can call it, what does it have to equal for equilibrium? 0. All right. Now, what's the reaction force? Yeah.
T prime.
T prime? Well, it's just a reaction force here.
Okay.
Yeah, so I guess if you want to call it T prime, let's go with what Alejandro suggested. So we get T prime. In this case, if we look at the circular shaft here, and we look at the rotation that T is causing, is that a positive or a negative torque? Negative, all right? It's ultimately up to you guys to assign the sign conventions, just indicate whether it's counterclockwise or clockwise at the end of the problem, all right? So we're gonna have -2 kilonewton meters, and then we add that to T prime, assuming that it goes the opposite direction or counterclockwise, and we get that T prime is just equal to 2 kilonewton meters clockwise. Now, one thing to note is if we were to cut a section directly through there, what is the internal torque going to be, T of x? Remember how we cut sections, we ignore everything to either the left or the right? What would the internal torque have to be?
Would it also be T prime?
It would be -2. The reason being is because then if we're ignoring everything here, then if we were to try and draw T of x and solve it using T prime, we would get that T of x has to equal -T prime, which is just equal to T. All right. I know it could be a little tough. It gets worse once we start getting into stepped shafts. All right. So T of x would just be 2 kilonewton meters, but negative. All right. Which in other words just means that the rod has a tendency to move counterclockwise, to move clockwise. All right. That's pretty straightforward since, this torque was already applied at the end. The only reason why I'm kind of like making a note of it now is because once we start again getting into stepped shafts, you need to know how to keep track of which direction each shaft is going to try and rotate. All right. So our internal torque is -2 kilonewton meters, or technically 2 kilonewton meters trying to move clockwise. All right. So now we just calculate our phi. We've got 2 kilonewton meters. I'm just going to put like CW, just to indicate clockwise, because I hate the negative. Yeah?
Why does it change in direction at T of x?
Equilibrium.
Oh.
Yeah, if you were to do some of the torques about the cut, then it would just be basically T of x plus T prime, but T prime is positive, which means T of x has to be negative, which just conveniently equals T. Does that make sense? Yeah. It's kind of hard to really visually see some of the torques because everything is kind of like, you're trying to draw torques that are in and out of the plane, and so it's kind of hard to see sometimes. All right, so anyways, 2 kilonewton meters. The position L we can call as a position X, all right? That's just the angle of twist at any point, right? Divided by G, which was 80 gigapascals, or 80 times 10 to the 9 newtons per meters squared. And then J was 1.021 times 10 to the -6 meters to the fourth. So we throw all of this in. And we basically get an angle of twist. Did I do that right? I'm just making sure. 2 kilonewton meters multiplied by 1,000 newtons per kilonewton, and then multiplied by x. Remember your units. And this basically just gives us a phi of x equal to basically 0.0245x, where x would be in meters. All right, so this really gives us the angle of twist of any position x along the length of the rod. So at x equals 0, the angle of twist of the rod is 0, which makes sense because it's fixed into the wall. At the far end, you just plug in x equals 1.5. And we should get that the max angle of twist is just equal to around 0.0367. Now let me ask this. What are the units of the angle of twist? It is radians. And if you want to get this in degrees, what do you got to do? Exactly. And that should just give you roughly 2.1 degrees. Make sense? Any questions about this or the applicability of it? No? All right. Let's do another example. Let's say now a torque of magnitude of 850 Newton meters. And in this case, the torque looks like it's applied counterclockwise. So I'm just going to write a little CCW indicating positive. Is applied at D as shown. The allowable shearing stress is 60 megapascals in each shaft. This time, we want to size the diameter that each shaft can be, given that the shafts can be solid. All right, so what do we need to recall? I also forgot to entirely do the shear stress problem here. Sorry, I'm like jumping the gun because like I'm yapping too much. So let's just really quickly, before we just jump straight into the next problem, how about we actually finish solving the second half of this problem, which is calculating the shear stresses. So for calculating the shear stresses, just use tau is equal to T times rho over J, where again the shear stress is dependent on the radial position of the shaft. So the shear stress is actually kind of constant. So what we get is basically 2,000 Newton meters divided by times rho over 1.021 times 10 to the negative 6 meters to the fourth. And so our shear stress as a function of the radial position is equal to geez, that seems like a large number. Roughly 2 times, it's roughly 1958.86 times 10 to the 6 times rho. All right, now we could just plug in tau max occurs when tau occurs at rho equals 30 millimeters. These seem like really large numbers. Am I like losing my mind? Yeah, because it's in Newton meters, newtons per meter squared, so the stresses are going to look large. Yeah, that's weird. 2,000 divided by 1.021 times 10 to the negative 6. So this would just be 1.958.86 times 10 to the 6. But rho should be in meters, since all of our units were technically in meters. Which gives us a stress of around, okay, that makes a lot more sense, 58.77 megapascals. I thought I was losing my mind there. Now tau min is going to occur when the shear stress is equal to 20 millimeters. So just carry that down, multiply this by 0.02 meters. And what we get is 39.17 megapascals. Okay. Any questions about this? No? All right. Now back to this problem. All right. So to solve this, what we need to know is obviously the max shearing stress. So in this case, we know that the maximum shearing stress tau has to be less than or equal to 60 megapascals. The applied torque T is 850 Newton meters. This is the same as saying 60 times 10 to the 6 newtons per meter squared. And we're asked to determine the required diameter of each solid shaft. All right. So the first shaft is going to be this rod here, CD. So let's solve for CD first. All right, so we just use the equation tau is equal to T rho over J. But in this case, what is our rho that we're trying to solve for? Where does the maximum shear stress occur? Where does the maximum shear stress occur? At rho equals what?
Would it be the 40 millimeters at the gear?
Not quite, because the 40 millimeters at the gear is entirely separate. It would the gears are only used to transmit force,
Okay.
but the rod
That's
itself
not, like, part of the
has-
body?
yeah,
Okay.
so not quite. What's the radius of this shaft? That's what we're trying to solve for, right? So it would make sense that the maximum shear stress occurs where on the shaft?
At the extreme, like, referred radius.
Exactly, at C. So max shear is at C. So what we need to do is say that tau is equal to T times C over J, which we could just write rho max is equal to C. All right, now J, that's just a property of the entire cross section. So J in this case would just equal pi over 2 times, I believe it should be 2 times C, if I'm not mistaken. Where was our equation? Yeah, the outside radius to the fourth minus A. So it would just be 2 pi over 2 times C to the fourth, right? Because C is our outside radius. So we can rewrite our entire expression to then just be tau is equal to TC over pi over 2 C to the fourth, which should simplify to 2T over pi C cubed. Now we want to solve for C. So C, just rearranging the equation, C should just be equal to the cube root of 2T over pi tau. Plugging in T and tau into the equation, we should just get that the minimum radius needs to be at least 0.0208 meters for solid C, for shaft CD. So what does that mean about the diameter? The diameter would just be 2 times C. So which would just basically be around 41.6 millimeters. So we could say use 42. Now what about shaft AB? Have you guys learned about what would the torque be in rod AB? Is it the same? No. You guys remember seeing stuff with gears and gear ratios and dynamics, I assume, right?
Not yet.
No?
We have
Man. All right.
We've been slacking this semester.
All right. But basically, how do gears work? I guess that's an important question that's really required for these types of problems.
You multiply by the input radius divided by the output radius.
Exactly, yeah. And that just comes from equilibrium, because then you're basically saying that the force that's basically felt at the teeth has to equal each other, which just conveniently is what you just said. That's what it works out to be. All right, so if we do some of the torques, or not some of the torques, but like some of the moments about rod CD, I guess some of the torques about C is equal to 0, we could technically get that the force in the I'm trying to word it better. I like how you said it. How did you say it again?
I mean, it's so you get. I just think thinking of a unit torque, I guess, or a unit moment, whatever the hell. Dividing it by the output and multiplying it by the input to for the change in radius.
Multiplying it by the input, dividing it by the output, or the other way around?
Yeah, because you're multiplying it by the big 100, and then you subtract, or you're dividing out that 40. That's
Yeah. All right, yeah. So basically, the torque in rod AB is exactly what he said. It would just be whatever the torque in rod CD is, and then you would just multiply it by the ratio of 100 millimeters over 40 millimeters. That just comes from gear ratios. So this would just equal 850 Newton meters multiplied by 100 over 40. Which should give us a torque of around 2,125 Newton meters. And then if you wanted to find the actual force that's transmitted through the gears, just divide the torque by that radius. So in this case, the total force is around 21,250 newtons. And that just comes from the F teeth is just equal to the 2,125 Newton meters divided by 0.1 meters. That's just the force through the teeth, in case you were interested. All right, so to calculate the total, to determine the required diameter that rod AB needs to be, we can just use that same equation. So C is just equal to the cube root of 2t over pi tau. the torque and the shear stress are constant, but when you solve for everything, just plugging and chugging, you should get that the required radius has to be 0.0283 meters, which, again, following that same rule, diameter is equal to 2 times c. Should give us a diameter of around 56.6 millimeters, so use 57. Any questions about this? No questions about this problem? Everyone understand the mechanism of the teeth? Awesome. I need to drink something up first. All right. Now we get into the realm of stepped shafts. So just bringing this up a little further. All right. So from statics, all right, we should be able to tell that the statics behind this would be like, let's say that this is like that shaft 1, and then this was that shaft 2. We know that the torque that's felt there and the torque felt here also has to be felt there and there, right? So the torque is just transmitted. Granted, it's a nice easy case because of the fact that there's only a single torque applied, but the same general rule would apply for several torques, which we'll actually get into in a little bit. All right, so that was the statics. For material behavior, we know that the deformation phi at B of rod AB minus the rotation at point A has to equal T times L1 over G1 J1. What does this mean? It's just the rotation at rod B for member AB, which conveniently phi A, guess what? That's 0 because that's a fixed end, right? So that's 0 because fixed. All right, but in a similar way, we can calculate the rotation at C for member BC, which would just be phi C, and then subtract that from B for member BC, which has to equal T times L2 over G2 J2. Now in this case, what is phi BBC and phi BAB? It's the rotation at point B in all instances, right? So the rotation felt by both ends has to be the same. So we can just simply say phi BC and phi AB, or phi BC and phi B for member BC and phi B for member AB have to be the same because of continuity. All right? That's all I'm trying to say. Lastly, we can just solve for it, and we can actually find that the total rotation at shaft C would just be equal to TL2 over G2J2 plus phi B, which guess what? Phi B is just equal to TL1 over G1J1. So it's just a summation of the rotations, all right? Very similar to when we were dealing with axial loads, you would just add the components of each sort of block that we were dealing with, where load was different. Make sense? Now, in the case of when we're dealing with a torque that has two different loads, I actually think I accidentally deleted that slide, so I would just say I'm going to erase all of this. and then I'm gonna reapply a torque here, and we can call this, I'll do an opposite direction just to make it easier. We'll call this TB, and then we can call that TC now. Whoops. All right, so statics would still just apply. Here, our compatibility equations would just be phi B minus phi A, which again is just 0. And that is just going to equal the torque in member AB times L1 divided by G1, J1. Now the torque in AB, if we were to do equilibrium at point A, then the reaction torque, I'll call this TR, would just equal to TB minus TC, or technically TC minus T. No, wait, you're right. TB minus TC. You guys agree with me on that? All right, and then if we were to cut a section through member AB, then the internal torque felt in rod AB would be equal and opposite to the reaction force. So that would mean that the torque AB is just equal to TC minus TB, which is just negative TB minus TC. All right, so the TB minus TC would just be negated, which is why you get the sign swapped. All right. Now for phi C minus phi B, which is the rotation at C minus the rotation at B. This is the total angle of twist for member BC. This also has to equal the torque in member BC times L2 over G2, J2. Which, guess what? If we were to cut a section through member BC and do force equilibrium for one side or the other, the torque in BC is just equal to TC. All right. So now we just can solve for the total angle of twist, C, which would just be TC L2 over G2, J2, plus phi B, which would just be TC minus TB, L1 over G1, J1. All right. Now the step will basically continue on infinitely forever and ever and ever for X amount of number of shafts. So the idea is just, it's the angle of twist is just the summation of the individual torques multiplied by each component's length, divided by the shear modulus of each block, divided by the polar moment area of inertia of said block. Keep in mind that each value of I is just basically block 1, 2, 3, and 4. All right. So it's just whatever shaft or component of said shaft you're interested in, because it could technically be one shaft of all the same material, but if you have several forces applied, it would obviously discretize that block accordingly. So it's basically just synonymous to saying how delta was just equal to the sum of Ni, Li over Ei, Ai, for I equals 1 to whatever value. I'll call it lowercase n. Make sense? So it's very synonymous to what we saw at the very beginning of the semester. All right? Are there any questions about this at all? All right. I actually kind of flew through that pretty fast to the point where the stuff from that I covered at the beginning for chapter 10, I was actually worried that was going to hold me behind. But yeah, that's pretty much it. Next class, we go into the fun stuff, statically indeterminate shafts. All right. I know how much you guys love statically indeterminate problems. So feel free to shoot me an email over the weekend. Otherwise, I have office hours right now if you guys want. Otherwise, have a nice weekend.